Hey there again. So I finally came around doing this third episode. I actually already recorded it, and I it took a long time. The video I recorded was almost an hour, and then the sound was not uh, there was no sound in the video. So yeah, I changed the recording software now. I'm sorry you're seeing it right now. My new recording software. It's a much better one from what I saw. Um, yeah, and we're going to do a video now. I wanted to show you the progress in the app at the moment. So this is the map generation at the moment. It's kind of running kind of slower right now. But I think it's the laptop, not the program itself. Yeah, so as you can see, it's a pretty nice map generation. We have cities all around. We have info fields. And I'm pretty much almost at the point I was, or rather, I am now at the point I was before I changed the map generation system. I also really I can show you a better view of the cities by doing the terrain toggle. So you can see the different cities in different colors and also the different cultures, which almost already look like small empires. So you see here we have a big culture group here in this river valley. The Bayahian, this is one big culture group over here also. Trestet Kelingayan, I guess that's from the Swedish culture generator. Yeah, and we have different cultures. The southwest coast, for example, are these Syshandian, and the north, these ones over here at the bay is the Minomayan. So yeah, that's the progress of the app. I just want to show you that one. Yeah, so let's look into what I did last episode, what I already wrote, and I will do it like the last episode. I just go through the code with you. I think that works well. Write me if you don't like that, or if you like that more than if I code it live. So basically, what I said in the last episode is in the last video was. If I remember correctly, I really hope I don't skip anything now. We did the interface, if I remember correctly. Yeah, that was the last part in the last video. We did the interface, and I talked a little bit about map generation. So I will make this a little shorter than last time. Basically, what happens at the moment in this map generation is that a random field is picked, and that random field takes the mean height of the field around it, the closest fields it has, and then varies that height, that mean, by a small bit, so we get these differences. That's how the height is calculated. I'm actually a little further now because the terrain is not solely calculated on height. I've got a second factor which I call humidity. It's not really a realistic simulation. I did a lot of research on stuff like how deserts are created in reality, and in the end I discovered it's just going to be too hard to do a realistic terrain generation system in the app. So I still think it looks pretty good now. So we have the forests or jungle, the green, dark green. We have the light green, which is just grasslands. We have this other green color, like this one, which is steppes. And we have the sand color, which is desert. And then we have the mountains over here. Yeah, so... Yeah, and the first thing we need for terrain generation, that's what I said in the video, is we need a tool which we will actually use very often, which helps us to find the neighbors of our fields. So basically what we will do is, if we have a field... Oh my god, it's really slow right now. It's not even zooming in. If we have a field over here where the hill is, we want to know what fields are, for example, in 3 fields range of that field. And that's what we will do in our... Oh my god. Yeah, it's really working badly right now. Don't look at it. We're just going to do this. It's probably also the recording software which slows the whole PC down. So basically, what are we going to do? We have this beautiful neighbors function over here, and that's what is new. And I'm just checking if I have a function which I can show you how this. Let's show you a function. So, that's the actual. That's the wrong command line. Let's take this one. Okay. So basically, we say Python 3 map.python, and as you can see, this is the graphical interface from last episode. But now what we have, these are all the neighboring fields in a range of 2 of a field with the coordinates 0, 0. Yeah, so our field is really small. It's only 9 by 6. We have the coordinates 0, 0 for our field. And these are the coordinates in a range of 2 in case our map ends and we don't wrap it around. So basically, if we want to test it, let's do it like this. We have the coordinates 1, 1, and we test it for a range of 1. Don't look at this. This is important. Now you can see we have 1, 1, and the next coordinates are 1, 0, 1, 1, 0, 0, 1, 2, 1, and 1, 2, which is correct. These are the 4 neighboring fields we are looking for. So let's see how we build this function. So basically, what we need to do, let's look at a little bit more theory. So this is how it looks. So this is the coordinate. This is the field on the coordinates. Sorry, 2, 2. So what can we do if we want to find out which the neighboring fields are? Yeah, I did a lot of stuff for you when in the video that was that had the error in it, and I'm really sorry. I'm not going to get that detailed again. But basically, you can see that the numbers, if we compare these numbers, they always add up to the distance of that field. So, for example, 2, 2 to 1 has a relative position of 0, minus 1, right? And 2, 3 has a relative position to our field of 0, 1. And 3, 2 has a relative position of 1, 0. And 1, 2 has a relative position of minus 1, 0. So that's working well. So what you can see now is that all these numbers, if we make both of these numbers positive and add them together, they all add up to 1. And in the second row, in the second phase, you can also see that is true for the next distance of 2. So the relative distance from 2, 2 to 0 is 0, minus 2. Then the relative position of this one is minus 1, minus 1. The relative position of 0, 2 is minus 2, 0. And so you see, if we make these positives, they always add up to the distance, so to 2 in this case. And now, how can we from that? So what is the best way to do this? Basically, when we have these numbers, from these numbers we can get a third number. Wait, how the hell did this work again? Yeah, so basically we have 2 and minus 0. Wait. Yeah, right. Okay, I will just explain you the code, and we will get further from that. It's kind of complicated, but it works really well and has a really good performance. So we will do it like that. I mean, the other way would be to make a recursive function, basically to say, we have this field. What are the neighbors of this field? And then you say, oh, these are the neighbors of this field. And then this field would say, and then you say for each field around it, what are your neighbors? And then it says these fields. But that's, as far as I know, that's more performance heavy than what we're doing right now. But we will also see this method with the recursive as soon as we have to calculate distances between two fields, because especially if we have to find paths for stuff like army movement, which is a long way still to go, but I would just want to mention it. There's this thing called Lie algorithm. So basically you assign each neighboring field a number, and then all fields with that number assign their neighbors a number, and then those fields assign their neighbors a number, and so on and so on. And then you just and as soon as you hit the field you're looking for, you can look which path is the shortest one. But we will you can Google it, Lie algorithm, if you want to see more about it. Yeah, but this is for the moment, this is a good algorithm to go with if we just want to know neighbors and stuff. So basically we create a function, define neighbors self n. N is the range in which we want to find the neighbors. We make a list of the fields we will return later. We could also do this as a iterator, which would mean we would, instead of return, we would write yield. Basically we would, at this point here, we would write yield neighbors instead of return. But because we never expect this list neighbors to become so big, it's filling up our RAM at once, because we never expect that to happen, it's not that important. If you would be concerned about big data, about that you don't have enough RAM to keep all the fields in this list at once, then an iterator is the way to go. But for the moment, this is easier, and yeah, this should work out fine. So basically, what we do here is for I in range 1 to n plus 1. So what's happening here? We say the range function, you know already, and n plus 1 is our distance. So let's say we have a distance of, so for our to try it, we say n is 3, okay? So basically what we do here is we count 1, 2, 3, 4. No, we only count 3, because as you know, a range only counts always counts one less than we write in here, which is a little, at first it's a little counterintuitive, but as soon as you recognize that range also starts at 0, it makes sense. So it counts 1, 2, 3, okay? And then we say for j in range 0 to 1 plus 1, to I plus 1. So basically in the first iteration, this counts. So in the first iteration, I will put it in parentheses, this counts 1. No, 0, 1, it counts. This counts 0, 1. In the second iteration, this is going to count 0, 1, 2. And in the third one, it will count 0, 1, 2, 3. Okay, and now combinations, then we create a set of the combinations we keep. We create this, we could also use a list here. A set is a little bit quicker because sets is a hash similar to like a dictionary. So it's not ordered, which doesn't matter to us. But it's quicker at retrieving the information. So it gets us a little bit quicker performance. And also it already filters out doubles. So because we always want to find each field only once, we don't need a list. A set is fine because we only want to find each field once. Yeah, so, and then we calculate this. So k is I minus j. So I here, for example, let's say we are in the second iteration. So, and then we have 2 minus let's say, for example, 0. 2 minus 0, okay? This means k is now 2. And now, by doing this, we will get a bunch of different coordinates for later. The first one is, the first coordinate we find is, and these are coordinates which are relative to our current field, from which we are using this method from. So j would be, in our calculation, j is 0. So this is 0, 2. In the next field, and now we get all the different types here. We all the different combinations on how these two numbers can be plus or minus. So as you can see now, from our two numbers, we have 4 different combinations on how they could be. 0, 2, minus 0, 2, 0, minus 2, and minus 0, minus 2. But now we have to find the actual coordinates of these fields to append them to our field. So basically what we do is we say for x, y in combinations. So we now take this set and we go through the set. Now we get the actual coordinates, we get the actual coordinates instead of the, what did I want to say? We get the actual coordinates instead of the relative coordinates. So we take our self.row, which is over here, self.row, self.row. Let's say we are at the coordinate 2, 2, like in our example. So now this is going to be 2 plus x. For example, if we use this one, if this is the first iteration, we will have 0, 2. So this is 2 plus 0. And this one is the column. So this is also 2. 2 plus 2. So this is 4. And this is, and this is 4. And this one is 2. So this is going to find the field at the position at the coordinates 2, 4. So if we go back to our example, we are here, and now we just found this field in this iteration. So if we go back, we see in the next iteration, for example, it would be minus 2, 0, minus 0, 2. This wouldn't make a difference actually. This would just find us the same field. Yeah, right. This is the reason also why we're using sets, because minus 0 and 0 are obviously the same number in the end. So this is also 0, 2. This will also find this field. And the combinations just will just recognize that this is the same one like the one we added before and not add it again. And then we have 0, minus 2. This is the more interesting one, because 0 minus 2 obviously gives us now minus 2 and 0 instead of, because this is, so this is minus 2, no wait, actually no, this is actually going to give us 2, 0. So this is going to be, if we look at our example again, 2, 0, that's over here. And now because for example, right now my map wraps around at this side. So basically, so like Civilization, for example, the map wraps around at the left and the right edge. While on the upper and lower one, it doesn't, because that would be very crazy and surreal. If it did, that would be a really weird form for a map. So now you can see here, to prevent the wrapping on the upper edge, we do this. We say if our x position, and if we look at the comments I set here before I deleted them, if we look at the x position, which is the height, we say if the x position is higher than 0 and the X position is lower than our self-game height. This is important because this says the field shouldn't be above the map and shouldn't be below the map. But it's fine if it's left or right. That works. And then we append the field. And we return the list we created by doing this. So I hope you understood this explanation. It's a little complicated, but it actually works. And yeah, as you can see, if we now do a test again on map.python, now that I explained this to you, let's go to the fields 2, 2, and let's take a range of 3. And we'll actually see now. So, and now we can, yeah, I'm sorry for not being able to make this bigger. It's fixed field size. I can, yeah. Yeah, so you can see this is all correct. Let's look into this one. So basically we have the field 2, 3, which is here, 2, 1, which is here, 3, 2, which is here, 1, 2, which is here, 2, 0, which is here, that's also correct, 2, 4, which is here. And we even have, we should even have fields on the other side of our map. Yeah, we actually do, because our field is, the dimensions of our field are 9, 6. So the field is 9 to this side. Or is it? I'm actually not sure right now. Because we have 3 range, so that means this is going to be -1 over here. So it should have... Or is it wrapping around at the top at the moment, maybe? No, it isn't. Wait, how many are these? These are... this is 3, 2. This is correct. 2, 1, 2, 3. Yeah, these are the four first ones, which are in the most inner circle. Then the next 2, 5, 8 should be the outer ones. 6, 8. So these are out there, which is 2, 0, 2, 4, 1, 3, 3, 3, 1, 1, 4, 2, 0, 2. Yeah, that's also correct. Ah, yeah, right. There is actually the one that wraps, because it's only one field which wraps around. Yeah, 2, 8. Because it goes out of this. Remind yourself, I don't know if you noticed, but I mixed up the coordinates. It should be the other way around. This is actually the y and this is the x. So this is 2, 8. So this would be over there. So this is correct. We have 2, 8 here. That's the one that wraps around. And we don't have this field over here. Because we don't wrap it. This is prevented by this if function here. And we could, if you don't want it to wrap it around on the sides neither, you could just do it like you could just do the same here and just say y position is smaller than self.gain.width, and now it will not. We have one element less. As you can see, it disappeared. It's gone. It's gone forever. Yeah. So yeah, the function is created. I hope you enjoyed it. I hope I can do more videos and more frequent now. Yeah, hope you have fun. Post questions if you have any. And check out the new version of the game on GitHub.